Hey guys, wish you all a very good evening. What's up? How's it going, guys? Hi Indradeep, good evening. Can you just confirm that you can read my screen? Awesome. Hey, hi Srinath. Glad you could join in. What's up? Nice. Rahul has given me the OTP for today. That confirms that you can read my screen. Thank you so much, Rahul. Awesome. So let's wait for more people to join in before we start our lecture. I hope you all are doing well. And before we start, just a quick announcement. So on 22nd April, there's a session with one of your peers who will be discussing the roadmap to crack data analyst offers, right? So it's always best to sort of learn from people who have already gone through the process of applying for interviews and stuff. So it would be nice if you could join in for this session. I'll paste the link and everything here, and it will also be available as a part of the class notes. So let me quickly pin this message in case you guys are interested. And yeah, cool. Hmm. Right. Sure, Amit. I will convey this message to the team. Let me just make a note of it. Cool. I'll just highlight this in a different color so that I know I have to convey it. Cool. I will convey this, Amit. It's an interesting thought. All right. We'll begin in about another 10-15 seconds. So let's get started. So we're here to study NLP, right? Natural language processing. It's essentially the data science behind trying to make sense of large corpus of documents. So let's get to it, right? Let's begin with a quick recap of what we covered last class, right? Uh, if you guys notice, there is a certain theme to machine learning problems, right? One of the major components of solving a machine learning problem is how do you represent your data in a way that a machine learning algorithm can optimize it. So broadly speaking, the core issue in not only natural language processing but a lot of other areas of machine learning is the pre-processing part, right? Uh, how do we convert? One moment, yeah. How do we convert text data into vectors? That is the broad problem that we are trying to solve. Okay. And the pipeline that we have been using in the last class is something we're going to revise. Okay. So essentially, generally, when we solve a natural language processing problem, we have a bunch of tweets or a bunch of text sources, right? These text sources in general are known as documents. Okay. So the smallest level of text that you want to uh, combine, right? The smallest level of text that you want to combine is basically a document. So for example, in the last class, we had studied how tweets work. Uh, the collection of all the tweets is basically known as the corpus of our data set, and each individual tweet is a document. Okay, so let us put ourselves in the position of Google, right? In the context of Google, guys, can you guys give me an idea of what would be the documents and what would be the corpus? Any ideas? If Google was doing this, what would Google call documents and corpus? Can somebody tell me? It's kind of obvious, right? Yeah. So the documents are going to be web pages. Okay. each web page that you find on the internet for Google will be a document. When we're doing tweet analysis, each tweet is a document. When we are doing something like papers, like let us say we want to build a tool which makes it easier for us to search for the latest research work which is going on, right? In that situation, each paper is going to be a document, and the collection of all papers over which we want to gain insights on, that will be the corpus, right? So broadly speaking, in natural language processing, we use these terms documents and corpus as follows. Okay. So in last class, we were doing tweet analysis. So the documents that we had were these tweets. The collection of all of them was our corpus. And what we did, right? What our task last class was basically to do sentiment analysis. So before we could actually do sentiment analysis on it, we had to solve this big problem of how to convert our text data into vectors, right? So let us quickly recollect how we did it last class. So in the last class, we started off by converting everything to lowercase. Any idea why? Why is this step necessary? Converting our entire text to lowercase? Yeah, ASCII, right? Because we don't want the to be separate from the, right? Or we don't want, uh, words that appear at the start of the sentence, right? Because of that, there will be capitalization. So these two words will be detected as different things at the ASCII level. So because of that, we wanted to convert everything to lowercase first, okay? So that we don't confuse our words. Then we wrote a bit of code to remove all the hyperlinks, hashtags, etc. Basically, all the extra characters which could interfere with our analysis, we removed those. Then we remove the stop words and punctuations and things like that, right? Can somebody quickly remind me what are stop words? What are stop words? So let's look at this sentence, right? Okay, is, am, are, exactly, Amit, right? So in this sentence, the stop words would be to, here, right? To would be the stop words here because it is something which does not really convey information. It is more to hold the sentence together, right? So that is the stop word removal that we did. And then we wrote something to remove the punctuations and other things which could interfere. Once we were done with that, we went for stemming and lemmatization. Why did we have to do this, stemming and lemmatization? Right. Yeah, exactly. Change and changing are the same, right? Yeah. Root words and base words. We want to make sure no matter what we do to our this thing, right? So basically, if you look at these three examples, eat, eats, and eaten, we technically want all three of them to be mapped to the same position in a vector, right? Because all three mean the same thing, but there are slight changes in these words because of things like you know tense or something like past participle and stuff like that. So because of that, we technically want to make sure all the same meaning words, or at least the root words, are mapped to the same location, which is essentially why we went for this. Once we did that, we built a frequency dictionary, if you remember, right? We wanted to see if a word is it appearing as a positive word in a document, or is it appearing as a negative word in that document? So we built a frequency dictionary, and then finally we built our frequency vectors, right? We had 1 comma pos comma neg, if you remember. This is the frequency vector that we used. Once we had this frequency vector, it was very easy to sort of do some sort of sentiment analysis, right? We simply did linear logistic regression last class to figure out whether the overall document had a positive sentiment or a negative sentiment. So this is what we did last class. And if you notice, a large part of the work that we did was basically to solve this problem, how to convert text to vectors. And this class is essentially a continuation of that idea, right? Before we can apply any sort of machine learning to our text, it is very important to convert it into a vector form. So today we're going to look at different strategies for how to convert text documents to numerical vectors, right? So the strategies broadly that we're going to discuss today are bag of words and TF-IDF. We're going to try and study how these things came up intuitively, and we're going to see how each solves the problem of the first, right? So we're going to slowly build our word representations. We're going to talk about what are the advantages or disadvantages of doing things in a certain way. And whatever we learn through this discussion, we're going to apply to a business case, right? The business case is broadly finding similar blogs. So are you guys familiar with this website called Medium? Are you guys familiar with this website called Medium? How many people have heard of it? Okay, a lot of people seem to have heard of it. Awesome. So if you guys know, Medium is like a very good source for people who write certain articles and publish it, right? So if there is a certain topic of interest, someone will generally go put an article on Medium. They will also tell you how much time it will probably take you to read that, right? So let's sort of visit a typical Medium article. So the information that is there on Medium's website is the author, the time that the author thinks it will take for us to read it, and the whole text, right? So as largely speaking, this is what a typical Medium document looks like. Okay. So the business case that we're going to talk about today is this, right? We're going to put ourselves in the position of the people who run Medium's website. If you notice, once I go to Medium's website, right, there is usually a lot of suggested articles. So once I've completed reading this article, there are other articles which it sort of suggests to me to read next, right? If you put yourself in the position of Medium, what they want to do is they want to maximize their revenue. So it is good for them if we are more engaged with their website and we follow topics which are related to each other. So broadly speaking, this is our problem statement. We are working as data scientists at Medium. Our job is to increase the engagement of a user. So once a user finishes reading one document, it's our job to recommend some related documents to that user so that whatever the user was reading, he can expand on that knowledge, right? So broadly, that is the objective which we're going to solve today, right? So this is kind of similar to the reverse image search from our computer vision classes, if you remember, where if I give you an image, you have to tell me similar images. So to some extent, the business case that we're going to solve today is the same thing, but with words. If I give you a document that I like, you have to tell me the documents which I may like based on my liking of this. Right? So this is like building a very simple recommender system. And we all know how recommender systems generally work. We have to convert our data or whatever suggestions that we have into a certain embedding format. That embedding is nothing but this numerical vector that we've been talking about. And then we have to calculate the similarity between these vectors. And that will give us an idea of what to suggest next. Okay. So are we comfortable with this? Any doubts up to this point? I hope few things are very clear to us, right? A couple of things that I just want to reiterate so that there's no confusion. Whenever we're doing NLP, the collection of the smallest items that we want to study are documents. The collection of all documents is known as a corpus, okay? So in the context of Medium articles, can you guys tell me what will be my documents and what will be my corpus? Can you guys give me an idea of that? In terms of a Medium article, what can I call a document? Can I call any one Medium article? Yeah, each article or blog is a document, right? So the text that is there in each document. So this text is one document for us. Yeah, exactly, right? And a collection of a lot of these is what will form my corpus. Cool. So now let us go and see what is the data that we are going to use to study this. Let's go and look at the data set that we have, right? Okay. So let's go through this quickly. One moment. Okay. Cool. So this is the problem we're going to solve. Let's quickly see what data we have. So generally, guys, if there is a website and there's a lot of documents, how do you pull that data out? What would you have to do to build a data set like this? Let's talk about that for a second. How would you build a data set like this? Web scraping, right? So web scraping is something that probably will be taught more in detail in the MLOps lectures. So until you learn that, it's not probably possible for us to scrape this in real time. What we're going to do is we're going to use some pre-scraped articles, right? So there is a website called Towards Data Science, which has already done this job of scraping web articles. It has basically compiled all the web articles that it has scraped into this single data set. And that is what we're going to use today for our work. Okay. So the source of this data set is here. I will be providing this providing this IPy notebook to you guys later. So you shouldn't worry about whether you have access to this data or not. Please try and follow along as I'm explaining, right? Okay. So this is what we're going to do. First, we're going to look at the data that we're that we have. Okay, so I have written some code here to download the data. We're also going to be exploring some features of this very popular library called Spacey. Okay, so Spacey is this library which is more suited for industrial needs. So NLTK, the library that we were using in the last class, is more suited for researchers. It is maintained by researchers and it contains a lot of implementations which are research oriented. So maybe not the best performing. What Spacey does differently is that it makes sure the implementations it has is state of the art. So this is one reason why it's probably better to use Spacey when we're doing NLP in the industrial setting, right? Okay, so let's move ahead. So if you notice, what we have in our data set is the link to the article, the title of the article, the subtitle, the author, the reading time, the actual text, like the actual textual content of the article, and the ID. Okay, cool. So we have this huge data set of, we have this huge corpus of various documents. Specifically, we have 208 documents with us, right? And there are 7 features associated with each of those documents. Cool. So this is the data that we're going to be working with. If we want to sort of visualize what one of these articles look like what one of these rows look like, we can use this very nice function called pretty printer from this Python package called pprint. Okay, so pprint stands for pretty printing. What it does is it will take a dictionary and it will sort of compact it so that it's easier for us to read, right? So if you notice here, we are pretty printing the first document that we have in our corpus. The author of this document is Sarang Narkhede. The ID is 2. The link is over here. The reading time is given to us. The subtitle is also there, right? So the subtitle is very informative about the main content of the article. So you don't have to sort of read the whole article to make sense of what it has. So these are the features that we have, and the text of the document appears here, right? And we also have access to the link of this document. So broadly speaking, this is what our data set looks like. Can you guys tell me, if you had to suggest an article, let us imagine that all of us were, looking at articles related to machine learning or data science or something like that. Generally, how would you do recommendations? What are the different ways we can do recommendations? Like if you had to solve it, item. Okay, cool. More views. Okay, that is one thing. Cool. I see. So one way is to look at the rating. The rating is basically given by the users who have already read the article. So that will give us some very nice way of classifying whether to read this document or not. Another thing is some people may have favorite authors. So if you know that, okay, this person is very knowledgeable, they have written about documents like this, which were very informative, we may have a bias towards the author of that, and we could recommend based on the authors. We could actually look at just the title, right? We could probably just look at the title and then form a recommendation. And finally, the most time-taking strategy is to actually read all the articles, form an opinion about all of them, and then give an overview to somebody, right? These are the different levels at which humans would solve it without the use of any tools. Now, the idea is we are going to try and reduce the time it takes to do the last strategy, okay? We're going to figure out a way to sort of reduce the time it takes for us to make sense of these documents and then suggest something, right? So that is the extra thing that NLP brings for us here. Okay, so let's see how to do that. Okay, so before we do that, let's look at the statistical characteristics of our data set. Very quickly, you have this articles.describe, which tells us all the main statistics of this. But we didn't really have many numerical columns, right? In fact, the only numerical column that we had over here in this data set, which makes any sense, is this reading time. Rest everything else, if you notice, is not a numerical column, right? So these mean, frequency, standard deviation, all these don't really have any meaning. But let's try and understand what the reading time of these articles look like. Okay, so let's take a look. So the mean reading time is 12.37 and the median reading time is 9, right? So there is a slight shift in the mean with respect to the median. What does this tell you? Like just this observation that my median seems to be slightly lesser than my mean. Does it give you any indication? Some articles have long reading time, right? So probably we have some sort of a skewed distribution. Exactly. I was looking for that word, Sumit. Perfect. So from this, just by looking at this 25, 50, 75, the percentiles and the median versus mean, we can say that it looks like the reading time of this is skewed, right? Okay, so let's confirm this by making a quick plot. Okay, so what we've done here is we've simply made a plot of the histogram of the reading times for these articles. Okay, in red you will see the median, in green you will see the 25th and 75th percentile, and as Sumit correctly predicted, we have a skewed distribution over here, right? Okay, it looks like most of the articles in our corpus can be finished within 20 minutes, right? Most of the articles we can say can be finished within 20 minutes. There are some articles which may take more than 20 minutes, like you have some odd ones here, and then in the extreme case you have 140 minutes as the reading time of an article, which is probably something very, very detailed or a very complicated study which comes over here, right? Okay. So coming back to the other features that we have, right? So these reading times are usually given by the authors, but it should be somehow correlated to something in our text, right? Can you guys guess what is that one thing this reading time should be correlated to with respect to probably the content of the article? Okay. Tim says someone did not close the tab. No, Tim. So guys, yeah, I'll come back to that. Okay, Indradeep says number of words maybe. Yeah, exactly, right, Indradeep? Because since we take more time to read longer documents, it's very, very reasonable to assume that the reading time given by the author is very correlated to the length of the text, length of the article. Of course, there are outliers. If there are a lot of mathematical equations in an article, I might take more time because I want to figure out what the math is like, right? So that could be one reason. But largely speaking, I would expect the length of my article to be kind of correlated to the reading time suggested by the author. Okay, so let's see if this is true. And indeed, we see that yes, this is true, right? If I look at the reading time and I simply take the length of the article, so I'm taking articles.text, okay, and I'm applying this lambda function where it is returning the length of this text, right? Simply this is exactly what I'm correlating to the reading time of this, and largely speaking, we observe this correlation here, right? So this is what our data set basically looks like. We have reading times which range from 0 to 140. Most of the articles are in the 20-minute range, and there are some crazy outliers like this one. And yeah, broadly, this is how our data set looks like. Now, let's proceed to the actual problem. Okay, let's proceed to the actual problem. Before that, let us sort of see a couple of intuitive things that we had discussed before, right? Like one thing that came up when we were discussing how would you suggest an article to somebody? Maybe authors who write similar, maybe authors write very similar articles, right? So let's sort of explore that. The question of whether writers usually write articles on the same topic, okay? So all we're doing here is we are printing out some articles written by authors who have written more than 2 articles, okay? So let's take a look. So you have this person called Daniel Jeffries who says how to crush the crypto market, quit your job, move to paradise, do whatever. Why people still don't get cryptocurrency. So it looks like this Daniel Jeffries guy likes crypto a lot. He writes articles about that. You have Alexander Nelson who's writing about Bitcoin, so which is kind of related to cryptocurrencies. You have Alan Farrington who's also writing about Bitcoin. You have some very technical articles. So you have Susan Lee who says, who talks about building logical regression models in Python, end-to-end projects on time series analysis, right? You have some random topics like Chernobyl and radioactivity, and you have a lot of data science like applications, right? Articles, hyperparameter tuning using random forests, etc. Right? So broadly speaking, it looks like in our corpus we have some articles related to Bitcoin, some articles related to economics, some articles related to Python, data science, some articles related to deep learning, maybe. So let's sort of see if we can find that. Yeah. So broadly speaking, this is how the topics are distributed in our corpus, right? So here's the deep learning articles by Ketan Doshi. Transformers explained visually part 2 and 3, right? So it's a very good thing that we have authors who write about similar topics. So now we know that our corpus has enough content so that we can suggest something to somebody. It's not random in the sense that, okay, We have 208 articles which are totally not related to each other, right? We have a corpus where we have this kind of demarcation between economics topics, data science topics, and deep learning topics. So broadly, this is one observation that we're going to keep using to check. Yeah, all drawn sample is good. Yeah, that is the correct takeaway, Akshay, right? So broadly speaking, we have a nice collection of data. We can expect some nice relationships over here. And these three topics that we have discovered, right? Try to keep them in mind. We're going to use this to debug whether everything that we have done today is correct or not, right? So one request is just keep in mind we have economics related topics, data science related topics, and deep learning related topics. Cool. Okay. So now we're ready to proceed. So coming back now, this gives us a broad idea of what a corpus looks like, right? Everyone comfortable with me using the word corpus now? No confusions there? Corpus, documents, these words should not cause any confusions today. Okay, perfect. Awesome. So let's move on, right? Now we'll come to the actual process of converting all our data into meaningful vectors. Right? Text to numerical vectors is what we have to do. Okay. And one problem that we hadn't discussed in this pipeline, right? One problem that we haven't discussed in this pipeline is something which is known as word contractions. Okay. So in the English language, sometimes in the flow of speaking, you will join two words, right? I'm pretty sure this happens a lot in Kannada, at least in Kannada, which is my mother tongue, this happens a lot. We tend to join words, or we tend to sort of, like while speaking fast, we will gobble up some words in between. So in the English language, the equivalent is this word contractions. So for example, you have this can't, which becomes cannot, which has to be understood as cannot. You have your, which is basically has to be understood as you are. You live, which is an extreme contraction where you will have is merged into a single word. So we have these things like contractions. And the problem here is that since they're a mixture of words, right? Generally, we have to make sure we can separate those two out so that we can give proper weightage to the words which are there in that, right? To get the contextual meaning, you have to convert it from this to this. Okay. And from a coding point of view, this apostrophe which is there, right? It's a special character. Generally, what will happen is you will remove these hyphenations and apostrophes and stuff like that. So once you do that, this can't will actually become a word can't, which does not make any sense. In fact, can't could mean canteen, could be a short for canteen, right? So some authors use can't as a short for canteen. So you may introduce some sort of problems in your representation if you don't take care of these contractions. So can somebody suggest what is the simplest way of getting rid of these contractions from a coding perspective? What is a simple strategy to get rid of this? How would you do it? Yeah, you would drop it. Okay, Akshay says, I don't even want to bother with contractions. I will simply ignore the word. That is one thing. Okay. Indradeep says replace. I like Indradeep's suggestion actually. And I like Riju's suggestion also. Dictionary kind of replacement, right? Okay. So let's discuss Indradeep and Riju's strategies here for a bit. So guys, your strategies are basically, I will now build a dictionary which holds all possible contractions, and wherever I see a contraction, I will map it to, I will replace that with those two words, right? That's the broad strategy. So we will have some sort of a custom mapping here. Like for example, this eat would become not, right? Apostrophe RE. Yeah, apostrophe RE. Okay, so Akshay says most simple one. Yeah, sorry about that. But coming back, it's important to maintain the information that is there in our text, right? So let's try to maintain as much information as possible. Okay, so this is like one example where you have these custom mappings. This will work, but do you guys feel this is exhaustive? Do you feel this is exhaustive? Not really, right? This is not probably covering all cases. So if I have a simple sample of text like this, let us see what happens when I do this, when I apply this mapping to this bit of text, okay? So I've decided to go to the party after all becomes, I have decided to go to the party after all. Why? Because we have this apostrophe VE, which becomes have, right? So this worked out, But let's look at the other parts. So he is not coming with us. He is not coming with us should have become he is not coming with us, but we don't have that in our dictionary here, right? So do you think it makes any sense to waste spend time building this, or should we just try and go for a library which will solve all our problems? Generally, how do we do things? We generally go to Python and we ask, okay, boss, has anyone written something which will help me with this, we'll go for the library. Okay. So we have this nice library called the contractions library, which is available in GitHub. So what we will do now is we will simply use this library to convert all the contractions in our document to the proper form, so that we can basically make sense of the text that is there, right? So that we make sure that we don't introduce random words and we don't lose any information because of simply dropping these contractions. So we'll use this library. Let's see how we do this. So expanded text equal to contractions.fix. So it's very simple. You simply say contractions.fix on whatever sample text that you want, right? Here my sample text is this collection of 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. 5 sentences. So let's see how this performs on this. So I have decided to go to the party after all. I will reach by 5 p.m. He is not coming with us. It is his birthday and he has other plans. They have thought about going to the movies. I will not be going to the movies. So all of these now have successfully been converted to the proper form that we can use to build our final representation, right? So we apply these contractions and get our job done. And in general, guys, whenever you deal with different types of documents, it becomes important to understand what are the problems that could come to my representation by some of my choices, right? So it's kind of important to keep this in mind while we are designing our pipeline, okay? What is a pipeline again? A pipeline is something which converts our documents and corpus to vectors, okay? That is what we're looking at here. We have detected this contractions problem with our current document. So we fixed that problem by using a library. That is what has happened here. Cool. Any doubts so far? Any doubts so far? This is a logical point for you guys to ask me questions. If not, we can move on, right? Now we'll actually start focusing on the problem of converting this to vectors. Okay, cool. So guys, from this pipeline, what all things do you think I should include to build my pipeline for analyzing the medium article corpus? What all should I use here? Should I have something which removes hyperlinks? This makes sense, right? Should I be doing lowercase? This also makes sense. Removing stop words, punctuations, this also makes sense. Stemming lemmatization, this makes sense. So now what we're going to do is we're going to apply all of these along with the contractions thing. Okay, so the new thing that we have introduced in this pipeline from last class is this contractions business. Okay, and that's what we're going to do. Cool. Now let's come to the main topic at hand. Now that we have pre-processed our whole thing, we've gotten rid of stop words, we've done everything possible. How do we go for converting these text as numbers? Okay, so the reason for that I think is very obvious to everyone by now. You can't do machine learning without vectors. So let's go ahead and see how to do that. So what I want you guys to remember right now is a few things. Okay, our job is to convert our corpus into vectors. So what should one vector be? Should one vector represent the whole corpus? Should one vector represent the document? Should one vector represent a sentence? Should one vector represent a word? These are your options. Which one makes the most sense? One vector, one document, right? Okay, cool, perfect. So we have this idea very clear. We're going to start converting all the documents in our corpus to vectors. That is our objective now. Okay, so this is what we're going to do. When we do this conversion, we're going to have a vector representation where the number of columns is going to be the number of words that we want to represent. The number of rows is going to be the count of the documents that we have in our corpus, right? So the dimensions of this matrix have to be clear to us. Let's keep that in mind and proceed. Okay. So what could be the simplest technique of converting a document into a vector? Let's talk about that. What do you guys think? If I have a sentence like this, right? The quick brown fox jumped over the lazy dog. Right? We have this example sentence. If I wanted to now think of this sentence as a document, okay, this sentence is now my document. I'm not considering the whole article as my document. I'm just considering the sentence as a document. What is the simplest way of converting this? Okay. More occurrences of word, less important. Okay, Rahul, you're jumping a step. You're jumping a step. Let's go patiently. What is the simplest way? I want to convert this to numerical. So typically, Vinay is here, right? Okay, Vinay says frequency. Fine. Let's look at that. Uh, this concept is sort of related to what we've done in feature engineering, if you guys remember, right? In feature engineering, we had categorical features. We used to convert them to numerical features by doing some sort of encoding, right? So when it comes to encoding, is one hot encoding something you guys are familiar with? One hot encoding? Okay, cool. Right? Okay. So let us now come from the concept of uh, converting categorical features to numerical features, see if we can do some sort of one hot encoding here. Okay. So for one hot encoding, I first of all need each position in my vector to mean something, right? Each position in my vector has to mean something. So what I'm going to now do is I'm simply going to take the words and I'm going to give them a position in this vector. So I'm going to say the over here, then quick, and so on, right? So for a single document, what I will do is I will essentially put a 1 if this word is present in the document. If this word is not present in the document, I'm going to put 0, right? Very similar to one hot encoding of images which contain multiple objects. So if an image contains a dog with a ball and a cat which is looking at it and a human who's throwing a frisbee, you have all these 5 objects. So in a 1000 object class, you would have ones in these 5 places, right? Same idea here, okay? Question is, how do I decide the length of this vector? How should I decide the length of this vector? Should I just look at one document at a time? Should I take more documents, or should I create one hot encoding vector for my entire corpus? Which is the best strategy according to you guys? How do I? The max one. So yeah, I will look at my entire corpus. Okay. I'm now going to start looking at my entire corpus. From that corpus, I'm going to look at all the unique words which are there in the corpus. Those unique words are going to tell me the length of this vector, and then I'm going to apply one hot encoding on that. Okay. Anyone have any doubts in this process? This is very straightforward, right? Guys, we've seen this many, many times. So it should not be too fast if I simply show you this code, right? Uh, let's take a look at it. So let's take this again, simple sentence, lecture on text representation. We can have, so if I now consider this lecture on text representation as my corpus, my document is going to be each word. I can then encode each document in this vector form, right? This is an extreme case where we're saying my corpus is the entire sentence only. Do you guys notice the definition of corpus and document is changing a lot? Are you guys paying attention to that? It's changing a lot, right? So generally, the definition of a corpus and a document depends on the application we have at hand. For this very simple example, we're saying the corpus is the collection of all 4 words. My documents are lecture on text representation. So how many unique words do I have in my corpus right now? How many unique words are there? 4? Okay, 4. So the length of each of my vector is now going to be 4. I'm going to have a one hot encoded version for each document that is there in my corpus, and this is what it's going to look like. Very straightforward stuff, right? Very straightforward stuff. So the entire sentence is then represented by combining all these individual representations together. Okay, cool. Now, this is kind of simple to do if we have things like Python, right? You can use Python to implement this from scratch, or you can use directly the one hot encoder from sklearn.preprocessing like we have done before, right? So essentially, we can use 2 strategies. We can do it by hand, we can hand code it, or we can use sklearn's one hot encoder to do this. Same idea. If I use sklearn's one hot encoder on this set of documents, so this is now my corpus, okay, where again my documents are single words. For this particular corpus, we have this kind of a representation which comes out. Okay, let's pause here and sort of talk about the drawbacks which are possible from this method. And I want you guys to first tell me what are the drawbacks you think are possible, and then we will check if we got all of them. How about that? So let's think about this. Okay, sparsity is one drawback. Okay, it's a sparse representation. Let's note this. Sparsity is one drawback. Anything else apart from sparsity? Okay, I'll give you a hint. Okay, let us say uh, he is a king among men. Okay, let's take this. Context or not float. All words have the same weightage. Okay, I'll note this down. This is excellent. All words have same weightage. So all words have weightage 1. Okay, this is yeah, lots of filler words. Okay, uh, cool. But Akshay, generally what we will do is before we apply one hot encoding, we will get rid of stop words. So for now, let's assume that's not a problem of this method, right? These documents, single words can also be whole article, right? Yes, Bishal. When we will apply it to our actual problem, we will consider the articles as a document. Here I'm considering words as document just to explore, just to explore. Okay, so let's look at this, guys. I want to now show you one very obvious problem with this. Okay, let us take the main words over here, right? King among men, right? These three are the main words. I can ignore these as stop words, right? So let's just take these three words and sort of see what the representation would look like, right? So I would have one dimension here for king. I have one dimension here for among, and I have one dimension here for men. Okay, cool. Guys, generally, how do we calculate similarity between vectors? What strategies do we have? Cosine similarity? Okay, we have cosine similarity. We can also calculate the Euclidean distance between these, right? Okay, cool. Now, can you tell me intuitively, king and men is related, right? Because kings are usually men. Kings are usually men, right? If it was a female person, it would be queen. So, okay, Akshay saying Hamming distance, that's also possible, Akshay, but let's keep that aside for now. I just want to show you one thing over here. Intuitively speaking, king and men should be related, right? And king and among also is, king should not be as related to the word among as it is to men, okay? And let us sort of try and figure out the angles over here, right? If we try and figure out the angles over here, what is the angle that we have between these different feature vectors? Angle is 90 degrees. Yeah. What is cos of 90 degrees? 0, right? Now, do you see a problem here if you use cosine distance? See a problem? You have this word king, which is kind of related to men. It's not related to among. But if I take this, if I take these three vectors, right? King 0, 0, 0 among 0, and 0, 0 men, right? I ideally want this vector and this vector to be related, but if I take the cosine similarity between them, it's going to be 0, right? Yeah. So somehow now the main problem with this one hot encoding is because we're assuming these dimensions to be orthogonal to each other, right? We're assuming these dimensions to be orthogonal to each other. When we take the cosine similarity between these words, it will by default give us 0, problem number 1. Problem number 2 is that it is not able to capture uh, relationships between related words, right? So largely speaking, this is one problem of one hot encoding, right? So similar words are not close by. Okay, let's now go back and see if we got this right. Okay, so cannot measure the importance of a word in a sentence. That is something you guys told me. All words have the same weightage. High dimensional sparse matrix representations can be cumbersome for memory. In fact, that is the first answer I got, which means I am talking to a lot of coders. Explosion in feature space by the number of categories. What do I mean by this? If I suddenly have a huge corpus of text which has almost all words in the dictionary and some words which are not even in the dictionary, right? There's going to be a huge explosion there. So the memory it takes to represent just one document is too large. Okay. And finally, the vector representations of the word is orthogonal and cannot determine the measure or between different words. So this is the problem that we encountered here, right? King and men should have been close, not close. So broadly speaking, if we simply follow this naive strategy of one hot encoding, right, we will have a lot of problems. So can we do better? Can we do better? Okay. Before we go better, before we go for something which is better in terms of representing our documents, let us first fix the obvious problems here, right? Let's fix the obvious problems here. How do we now make sure that this is not occupying so much memory? It's a sparse representation. Generally, guys, how do you solve this problem of representing sparse data? How would you do it? Anyone? It's a computer science problem, right? Yes, perfect. Indradeep says create a dictionary. Instead of storing all the zeros here, I will simply create a dictionary for each document which is there in this matrix. What I'm going to do is I'm simply going to say, what are those features which have one over here, right? I can represent this entire sparse matrix as a collection of 1, 2, 3, 4, 5, 6, 7 dictionaries over here, right? So that is how we can do it. So one obvious way to optimize one hot encoding is to store only the indices in a dictionary, okay, to save space. Can we do this? Can we further optimize this? Further optimization now would involve not only keeping track of how many, not only keeping track of whether this word has appeared in that document or not, right? The other thing that I will have to do is I have to also record how many times it has occurred in a document. So let us take a random Medium article, okay? Let us say it is on deep learning. Do you think the word neural network or the word neural, do you think it will appear just once or will it keep appearing many times in that article about deep learning? What do you guys think? It will appear many times, right? Okay. So generally one more way to sort of optimize this one hot encoding representation in terms of this problem, right? In terms of importance of the word in the document or the sentence. So to solve this problem, what we can do is we can now stop recording it, stop thinking of it in one hot encoding form. We'll in fact start measuring how many times this word has occurred in that frequency. So with these two changes, right? These two changes, what we get is what is known as the bag of words representation. Okay. So the bag of words representation typically does the following. Okay. So let's understand this better. So now our discussion so far has led us to this bag of words representation for my corpus and for my documents. So we have bag of words representations. Okay, cool. So let's understand this bag of words representation. What is given to us is a corpus which contains many documents, right? So we have doc1, doc2, etc. till doc n. Okay. What is the first thing we do? You guys had told me this a few minutes back. Can you guys quickly remind me? What should I do first? I should first look for the what in these. Should I look for the unique words in these documents? Yeah, all unique words. So step one would be to get all unique words from the corpus. Step two would be put these unique words as the column names. Step three would be for each doc, right? For each document in my corpus, find frequency of words and store in the matrix. Very straightforward, very simple. Bag of words representations is this. You take your corpus, find out all the unique words, create a vector out of it, and in the entry of the vector, you store the frequency of that word. Okay. This is how we create a this is how we create essentially a bag of words representation for our corpus. Okay. Amit has some suggestions. Okay. Amit says, okay, hold on. I think we skipped a few steps here. Before we go for this step, Amit's suggestion is do the following, right? We can also apply a pre-processing pipeline before we go for this. Right? Things like lowercase, stop word removal, then things like stemming, lemmatization, etc. Right? So whatever pipeline we have, it's probably a good idea to put this there before we go ahead with this, right? So guys, both ways are correct. There's nothing preventing you from directly doing it without all the pre-processing. You can do it this way also. Both will give us essentially a vectorized representation for our documents. And the problems with this bag of words representation is something we've already seen here, right? Whatever problems were there with one-hot encoding, same things will carry on to bag of words representations. For now, because generally guys in NLP companies, what happens is people will probably ask you to implement this from scratch, right? So a good way to test whether you're a good coder as well as know the concept well, right? What people could ask you to do is implement this from scratch. So maybe someone will say, okay, implement a bag of words representation. You will quickly go and do it. Then they will say, actually optimize it using sparse vectors. So the optimization using sparse vectors would be basically to create these dictionaries, right? So these kinds of implementations is what they would ask you. Let us go through these. Let us go through these implementations now. Okay. Before I go ahead, there's a doubt. Can you please show the matrix how it will be stored? Sure. Sure. I'll show you that. We're going to take up examples soon, Akash. So we'll see it then. Okay. So let's go ahead. First, create a vocabulary from the corpus, right? Exactly that. Get all the unique words from the corpus means create a vocabulary. So this is, what is a vocabulary? It is nothing but the collection of all the words we know, right? So all of this. Now the example that we're taking is these three sentences. So for now, to show you how a bag of words representation is built, we're going to consider these three sentences as our documents. Okay, this is our corpus, which contains these three documents. And let us see how we do it. So if I now take these three sentences and try to find the unique ones there, this is what I will have. I will get these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I'll get these 11 entries. Okay. So 11 is the size of my columns in that bag of words representation. Now we're going to construct a one-hot encoded representation of the words. So Akash, this is exactly what you were asking for, right? How the matrix will be stored? It will be stored like this. You have this word it, okay? The first sentence is this, right? It was the best of times. This is our first sentence. So for this sentence, the representation that we have is like this. So this will essentially be our unique words, our vocabulary. This will be basically each word encoded as a vector. And this is an example of that. Let us try to see if we can do this at a sentence level, right? So these representations are at the word level. Let us see if we can do the same for sentence level, right? Okay. For the sentence level, we have to add one step here, right? We have to combine the one-hot encoded representations for every document. Depending on how we are combining, we will get two types of one bag of words representations, right? So if we use binary OR operator over here, so if I take these columns and I apply an OR operator over here, it will be 1 if any one of these is 1. It will be 0 if all of them are 0, right? In that case, I will get the first version of my bag of words representation, which is only indicating whether it's a word is present or not in the sentence, right? So that is what I will have. If I instead use the sum operator, it will actually calculate the frequency, right? It will calculate the frequency if I use the sum operator for my entire sentence. So based on this, let's see now. Okay. So over here, this is an example of using which one? Which one do you think I used over here to create this? Did I use summing or ORing? What do you see here? I used OR. No, Indradeep, I did not. You see that frequencies are there now? I used sum over here actually. So for this representation, I have used the sum. So I'm actually getting the frequencies over here. So let's take a look, right? It was the age of wisdom and the age of foolishness. So the word the appeared 2 times, here and here, right? Which is why we have 2 over here. So if we use the vector sum operation to combine all of this into one representation, we get this thing, right? We get this kind of a thing. And this is most popularly used for simple applications, right? For simple applications like looking for similarity between answers or stuff like that. Generally, people use this bag of words representation to do stuff. So again, guys, these things are very heuristic, and it's important to understand what was the thought process that went into getting these things, right? Okay. So with that now, let's proceed. So a custom implementation of bag of words is what we're going to discuss next, right? Generally, if somebody asks you to do this, how would you go about it? So we have this corpus which contains all our documents. What we're going to do is we're going to first build our vocabulary. We're going to take advantage of the Python set function to do this, right? So the set will make sure that only unique words are kept there. Then for each sentence in my corpus, the sentence representation is a dictionary like this. Why is it a dictionary? It's because I want to make sure, okay, so I'm basically building this dictionary to build one empty vector here, if you notice, right? This is an empty vector over here. Now, in this empty vector, I will keep updating the frequency over here, right? I will keep updating the frequency over here in this loop. And that is how I get my bag of words representation. So very straightforward, this is what we get. An alternative to this is we can directly use something from sklearn. We can use sklearn's count vectorizer, which basically does everything that this does and also gives us some additional functionality. So there's a very good reason why to use this count vectorizer. Everything that I was talking about, right? Everything I was talking about in this pre-processing step, this count vectorizer will actually give us options of doing these things before applying this count vectorizer. Okay. So if you look at the documentation of count vectorizer, right, it has a lot of parameters which are very helpful. So for example, look at this lowercase equal to true, right? This lowercase equal to true actually asks the count vectorizer to make sure everything is lowercase before you apply this. Similarly, we have this tokenizer option. We have this stop words option. All of these options are already built in. All you have to do is specify what pre-processing you want it to do, and it can do it for you, right? So in general, if you want to avoid writing a lot of code to build your entire pre-processing pipeline, count vectorizer is a very good option. Okay. So how do we do this using count vectorizer? We simply create an object of it. Make sure that if you wanted to do something like stop words, you put it in the right place over here, right? Now, once we have this object ready, we will apply fit transform on our corpus. We'll say too dense so that it becomes a matrix rather than that sparse representation that we had. And finally, we get our bag of words representation. We create a data frame out of this, and this is what we get. Okay. If you notice, the output here and the output here should be similar or should be exactly the same, which is my guess. The only difference, I believe, is the order in which these words are appearing. So if you notice, the order here is quite random. The order here is alphabetical, I believe. So that's the difference. Okay. So we've seen a library function which does all the steps. It also gives us some additional functionality. And this is where I'll pause for questions. Okay. So anyone who has any doubts up to this point as to how to build a one-hot encoded representation, how to build a bag of words representation, this is the time to ask me, right? I already see one doubt. Second representation looks like frequency count. Why is one-hot encoding needed? One-hot encoding is needed to basically get these individual vectors first, right? You first want to encode the words and then combine them to get one vector for the entire sentence. So it is just a matter of breaking it down into 2 steps. It is not necessary. I mean, you can sort of skip this step if you write the right line of code. This is just one way to look at it so that we know how to get the binary version of it as well as the frequency version of it. That's all. Just to make that clear, we broke it down into 2 steps. Cool? Cool. Okay. Okay, guys. Looks like there are no further questions. So let's continue, right? Let's continue. We now saw what the bag of words representation is, how it is encoded. and we saw 4 problems. Out of the 4 problems, we have dealt with 3 of the problems, right? We have not dealt with one of them. We have not dealt with one of them, which is basically that angular thing. And we have also not probably dealt with the frequency weightage thing, right? Right? Uh, Guys, if we use the frequency method, when will the weightage of this be high? When will the weightage of this be high? So, okay, let me give you a concrete example. Okay, let me give you a concrete example. Issues with bag of words, unresolved issues. So now I'm just going to talk about the unresolved issues with bag of words. Okay. Did we solve the efficiency thing? Did we solve the memory and time efficiency thing? Yes or no? We solved it? No? How? We solved it, right, guys? We converted it to so we okay. Let me rephrase my question. Do we know how to solve that? Do we know how to solve the sparsity and memory issue? We simply convert it to this thing, right? Okay. So that is why I'm saying let us assume we know how to solve that. What are the things we have not solved, right? That is what I want to sort of focus on. So we have not solved the weightage issue, okay? And we have not solved the angle cosine similarity issue. Okay. Now let us focus a little bit on the weightage part first. Okay. So guys, can you tell me in this bag of words, the frequency version of the bag of words representation, uh, when will a word get high weightage? When it occurs many times in a certain document, right? Okay. So for example, we have a document which is basically a deep learning paper. Okay. I'm going to give you 3 words. Okay. According to you, which of these words will occur the most? Which one will occur the most in this deep learning paper? Network, okay. Network will have the most. Let's say 1,000 entries. Neural, let us say 800 of them, right? So 800. So most of the times, let us say neural network appears together, but sometimes they just say network architecture or something like that, right? So network appears the most. Then we have neural. Residual, do you think it will appear a lot? If it's a ResNet paper, it might appear a lot. If it's not, then probably not. Let us keep this at something at 50. Okay, cool. What I want you guys to understand here is neural network residual, the maximum weightage is going for this word network, right? But we already know that this is a deep learning paper. The word network should not have that much weightage, right? In fact, if you notice, the word residual tells me something very important about the paper. The term residual, if it appears in my deep learning paper, what does it tell me? It tells me that this paper is somehow related to ResNet, right? So what is interesting here is this word residual gives some important information here. Okay. So our strategy of using weightage as frequency is probably wrong. We have to now think of different ways of applying weightage for these words. Okay. And that is what brings us to this broad strategy called the term frequency and inverse document frequency. Okay. So now we are going to learn a certain way of adjusting the weightage part in our bag of words model. Okay. We are now no longer going to use the frequency over there. We're going to try and develop some number, some measure, which allows us to basically uh, gain more information about the papers, right? So for example, if the word residual appears here, it is informative because it tells me that there is ResNet appearing somewhere here. Okay, cool. So that's the broad idea. I'll pause here. We're going to look into this more. So if you're not understood this logic, we will discuss it further. But apart from that, if you guys have any questions, now's the time. Let me quickly take a couple of questions which are there. Amit says, but frequency will be high for word on which document is based. Yes, Amit, right? Yes, I totally agree. But what we generally want for a word is that word contributing or representing something important about this document, right? Right now, it is just based on frequency. But there are so many words which appear very frequently because they're related to the topic. Whereas something which describes the topic like residual in a deep learning paper, that will have more weightage, right? If you tell me there is the word residual in a paper, I can interpret that, okay, there's resonate happening somewhere. So that is essentially the what I'm going after. I no longer want these weights just to tell me if they're appearing frequently. I want these weights to tell me, okay, this is appearing frequently, but with respect to my entire corpus, right? With respect to my entire corpus. So if you notice, these weights are sort of at the document level, but they're not telling me anything about how this document is with respect to other articles in the corpus, right? Our problem is to suggest other articles, not just one this thing. So not just one document. So we want to now adjust this weightage based on the information that it contains. Okay. So Amit's this thing is we should reduce the weightage on this. Let us see how to do this mathematically. So Amit, love your intuition. We should reduce the weightage for the most frequently occurring words if they're somehow related to the main topic of this, right? So how do we solve this problem mathematically is the next discussion. And we're now going to discuss this TF-IDF, okay? So first, let us look at what TF-IDF is defined as. TF-IDF is a very popular technique for us to get feature representations in a bag of words model, okay? So TF-IDF is not anything separate from bag of words. It's very, very related to bag of words. The only difference is TF-IDF adjusts how the weightage is given to these words in that, okay? So let's study this now. My TF-IDF is defined as term frequency into inverse document frequency. So let's pause here and understand what this means. Okay. Term frequency measures how common a word is in the document. Inverse document frequency measures how rare a word is across the corpus. Right. So now, before what we were doing was we were using the term frequency. Right. We were using only the term frequency, if you notice, in our bag of words module. Everyone see this? Our current understanding of bag of words is we only put the term frequency there, but we have to now change the weightage so that it tells us how does this document compare to all the other documents in my corpus, right? Is there something special about my document, or is it just another common article which is there, right? So that's the basic motivation for TF-IDF. Okay. So now let us try and understand how to calculate this TF-IDF for our corpus. Okay, cool. So let's get into that. Before we go there, do you guys want a break, or is it okay if we continue? This is a logical point for a break, right? Because TF-IDF is a little bit mathematical. We're going to spend some time on this. If you guys feel like you need a break here, please hit yes. If you feel you can continue, please hit no. I will go with the majority. No opinions, guys? Okay. More people want break. Okay, let's do that. Let's take a short break over here. Once we come back from the break, we are going to understand how to adjust the weightage of our vector representations, so that it not only tells us how is that word in the uh, how is that word in that document. We also want to now calculate how is that word with respect to all other documents which are there in my corpus, right? Okay, so let's come back to this. Okay. So setting a timer here. I'll see you guys in 5 minutes. And we're back. Cool. Quick check. How many people are back? Okay. One person saying he's not back. Okay. Okay. Some people are back. Hopefully the others are as well. Let's continue. Right? Cool. Let's continue our discussion. So what have we seen so far? We've seen how to create a bag of words representation for our documents. Uh, we had an issue with the weightage of the words over there. The number over there was giving us frequency. Now we want to adjust that number so that it tells us how important that word is in the corpus rather than in the document. Right? That's the idea here, which is why we define this TF-IDF. You have this term frequency, which is the old way of doing things, and you have this inverse document frequency, which is going to give us some information about how important is this word in my whole corpus. Let's look at it now. So first, let's focus on term frequency, right? Term frequency is straightforward. You have the frequency of how many times that word is occurring in my given document. Okay, cool. Now, is it a good idea to leave that vector at a very high value? Frequency of a word can be very large, right? If you imagine a medium article, the frequency of a word in a medium article could be somewhere. So let us assume it's like 1,000 length medium article, right? You could have some words which occur hundreds of times, right? So it's probably not a good idea to leave the magnitude of your entries to 100,000 in that range. So generally what people do is they will take this term frequency and they will convert it to a probability value. Okay. So if you notice the definition of TF, T comma D over here. Okay. Why is this TF of T comma D? T over here, guys, stands for the term that you have. D stands for the document that you are considering right now. Okay. So the term frequency for a certain document, the term frequency of a term in a document is defined as the frequency of that term in that document. Okay, that is what this ft comma d means. And in the denominator, we're going to have the sum of all possible terms in that document. Right? This is nothing but the length of the document. Right? So in some sense, now the term frequency that I'm defining as the weightage that I'm giving to a word, okay, it's going to be defined as the probability of finding that word in that document. Is this point clear to everyone? Are we all clear on what term frequency now means for us? It is the probability of finding a certain term in a given document. That is what term frequency T comma D is. Cool. Now let's move on and see. So guys, generally what happens is different research papers will redefine their values. Okay. So that we understand. Okay, there's someone who has not understood something. Okay, hold on. I need to pause here. Amit, is there a doubt at this point? I just want to understand. Have you understood this part? Okay, I'm going to assume that you understood this part, and I'm going to continue. Basically, we have this definition of term frequency as the probability. Oh, okay. Amit says, can you explain representation? Sure. Okay. So Amit, the idea is this. Let's go back here to this one. Let's go back to this example. If you notice, these are the words that my count vectorizer is returning, right? So do you agree that this is the representation of my words and these are my documents? So this is my representation for the whole corpus. Okay, cool. Now, what I'm saying is I'm going to change this representation simply by taking the first row. Okay, I'm going to take the first row. I'm going to divide this each entry in this row by the number of words in this row, this document. Okay. So now how many words do I have here? I have 1, 2, 3, 4, 5, 6, right? I have 6 words over here. So what I'm going to get for this entry best, which occurs one time over here, is 1 by 6. Similarly, times occurs one time over here. So this is going to be 1 by 6. Here, worst of times. Times is going to be now 1, 2, 3, 4, 5, 6 again. 2, 3, 4, 5, 6. Yeah, 6 again. So I'm going to adjust this by replacing it with the probability of finding that word there. So that is how I will change my representation if I start applying term frequency over there. Only term frequency. But we have not yet covered inverse document frequency. So let's come back to that. So before I go to inverse document frequency, I just want to point out one thing to everyone. Generally, guys, what happens is when people write research papers, right, they will take these very common terms. Things like term frequency is used left, right, center in NLP. most researchers, they will try to redefine it to suit their problem's needs. Okay. So there are some variations that we have to be aware of. Okay. Let us look at all other variations of what this term frequency could mean. But for our understanding, this is what it's defined as. But so that we don't get confused when we're reading research papers, we have to understand what are the different ways people think about this. So let's go through that. Okay. So first option is using the raw count itself. This is exactly what I told you before, right? In that old bag of words model, if I simply use the frequency, that is also valid. Next option is using Boolean frequency, right? Boolean means what? 1 if it is there, 0 if it is not there. This is also very straightforward. We already saw this. Cool. Any confusions up to this point? The next two are kind of confusing. So I just want to confirm. Are we clear till here, guys? Have I put the class to sleep? Come on, guys. A little bit of interactivity will go a long way, right? I hope you guys are not sleeping. And yeah, okay, cool. So let's quickly revise. Term frequency can have multiple definitions. One way to define it is probability. This is what we will be using for our work, but we have to be aware of how other people call this. Raw count is something we've seen. Boolean frequency is something we've seen. Another option is to simply apply log, right? We can do a log transform. Guys, when do we use a log transform? When do we generally use a log transform to convert our data? Can you guys give me some examples? If I simply take the frequency, add 1 to it and take the log of the whole thing. Yes, perfect, Indradeep. So generally what happens is if we are studying very, very large documents, right, these frequency terms can go very crazy. So if you're studying things like websites, where a website can have something like 10,000 words on a single web page, there the frequency counts can go very high. So what we do is we will apply a log transform so that we can bring down the range, right, before we apply our machine learning algorithm. So this is what the log transform does. Any idea why I'm doing 1 plus FTD? Why am I doing this 1 plus? Is log of 0 defined? Log of 0 is not defined, right? Yeah, log of 0 issue. So I want to make sure that this 1 is making sure that this log does not go to minus infinity. Okay, that is why I'm doing this log of 1 plus FTD. So this is how people generally define it. And finally, we have an augmented frequency to prevent bias towards longer documents. So sometimes what may happen is if your documents in your corpus are not of the same length, right? Just because one word occurs a lot in some document might place unnecessary importance on that word. So to adjust for that, what people do is instead of putting the total length of the document in the denominator, they will put the maximum occurring term in the denominator. So all I'm doing is I'm changing the denominator here so that, if I have a very long document, I don't get very small probability values. An example of this is just what we saw here, right? So if you notice here, we have these two sentences which are of length 6. This sentence has length what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? So if you notice, this word age will now be 2 upon 11, but that penalty is too much for this, right? The only reason why best and times got less penalties because they were appearing in documents which are of length 6. So instead what we will do is we will divide this by the most frequently occurring word in that document. So let's go back and see this. I have max of f of t prime comma d where t prime belongs to d, right? Here d is my document. I will essentially take the most frequently occurring word, take the count of that, and I'm going to put that in the denominator instead of the total thing. And of course, I will apply this 0.5 plus 0.5 into this because I want to make sure this is in a reasonable range. I want to make sure that this is roughly centered around 0.5. So I will make this adjustment here. Okay. So broadly speaking, this is how term frequency works. Okay. So if I had to do term frequency for these words now, this is how it will look, right? I get 1.667 because I'm doing 1 upon 6 over here. So that is why I'm getting this number, and similarly the other numbers. And if you notice here, age has a much lower value here, right? It is age occurs 2 times in this sentence, but it has a value which is very close to this 0.167. So if I wanted to fix this issue, I would have used this definition of this. Okay. So applying term frequency only to our representation, this is what we get. Now let us see what is inverse document frequency. Okay, cool. Okay, so before we go to inverse document frequency, let us understand the setting a little better. Okay, I have doc1, doc2, doc3, doc4. Okay, let us say this doc is 100 in length, this doc is 50 in length, this doc is 700 in length, and this doc is say 300 in length. Okay, we have these documents. Let us say that one of these documents is special. These three are very similar. This is also similar, but more important. Okay. So if I had to give you a concrete example, you can imagine these three are deep learning papers on computer vision, papers which apply VGG16. Okay. And this is a deep learning paper which applies ResNet. Okay. This applies ResNet. First of all, guys, can you tell me the total number of words I have over here? Total number of words will be nothing but the sum of these, right? So the number of unique words I can approximately say could be somewhere around, say, 200. I can say that there are 200 unique words in all of these documents, right? Using this example, let us try and understand what is this inverse document frequency. Okay. Now, inverse document frequency takes three inputs, if you notice. It's taking T, D, as well as C. Okay. This is new because term frequency did not take C. Inverse document frequency is taking C. So what is C? C is nothing but the corpus that we have. Okay. The corpus is nothing but the collection of all documents. This is the corpus that we have. My inverse document frequency is nothing but log of number of words inside this document. Okay. So you can think of this D as a set which contains many words. The cardinality of this set is given by this mod of D, right? So this in the numerator is the total number of words that are there in my current document. In the denominator, I basically have a count of how many documents are there in my corpus where this word T appears in that document, right? Okay. So guys, can you tell me the word residual? Do you think it will appear in these three documents? These three documents use VGG16, okay? They don't know about ResNet. So residual will not appear in these three words, right? Okay. But residual will appear in ResNet. I mean, the whole word ResNet means residual network, right? Okay. So residual appears in this. So let us now see how to calculate this IDF for, so let's do this, right? IDF of residual in these documents. So if I take these and I call this D, this will be my, let me say this is D1, this is D2, this is D3, and this is D4, right? This whole collection is called C actually. It's the corpus, and I have these. I want to calculate the inverse document frequency of the word residual with respect to document 1 and with respect to this corpus of these collections. Can you guys help me calculate it? Let us say residual appears one time in this paper, just once, right? Okay, so let's do this. So what I will first do is I will put the count of this over here. So what is the count of D1, guys, here? What is the count of D1? 100, right? I have 100 words in this document. So 100 is the length of this. Now I want you to tell me the denominator term, right? I want you to tell me how many documents are there in my corpus so that this term appears in the document, right? How many documents are there in my corpus so that the term appears in it? One only, right? This is just one. Why? Because it is appearing only in this document and not in these, right? So 1 is what I'm going to put in the denominator. So 100 by 1 is what it is. So it is 100, okay? That is the weightage of this. Now let us assume the word neural. Let us now calculate the IDF of network actually. Let us use network because I'm guaranteed to find network appearing in these, right? Okay. So for simplicity, let us assume the word network appears 25 times in all documents. Okay, 25 times in all documents. If it appears 25 times in all documents, can you guys now calculate the IDF term over here with respect to D1? Let's calculate it together. Okay. So now I'm calculating the IDF of this word network. Okay, not of the word residual, but of the word network. So let's see. How many words are there in the document again? In the numerator, I'm going to have 100, right? Because this document 1 has not changed. In the denominator now, I want you to tell me how many times, how many of these documents are there which have the word network in it. How many are there? 4, right? It's there in all 4. I'm assuming that it appears 25 times in all of them. So this is what I'm going to have. So this is going to be 4. So the value is 25. Okay. So 25 is what this comes out to. So for residual, the IDF is 100. For network, it is 25, right? Okay. So what do we learn from this? Why is it that this word residual is getting more weightage than this word network? Let's try and understand this. This will solidify the idea of why we use this IDF. Okay. What is interesting here is this word residual. Yeah, it's there only in this doc. Akash, you're absolutely right. It's there only in the doc, but it is also a measure of how probable it is to find this word, right? If you notice, this is also a probability term, right? This is also a probability term. It is a flipped probability term because this should ideally appear in the numerator. This should appear in the denominator, right? That is why we have this inverse document frequency. So if we had to now think of this as a probability term, what this IDF is telling me is what is the probability of finding this word in all my documents, given that my current document's length is this much, right? So in some sense, we are calculating the importance of this word inside my entire corpus. Okay. So a higher IDF will basically mean that this word is very important to one document as opposed to the rest, which means that it helps us identify unique documents. So a higher IDF score basically means that it is more unique and it should probably have more weightage in deciding something. Okay, that's the idea. That's the idea behind IDF. Cool? Okay. So now that we have this, let us discuss the variants here. The first variant I'm going to notice is this log. Why are we applying log? Again, because we want to bring the range down, right? If you notice, this is an inverted probability term. So if we just focus on what is inside the log, this value can go from 1 till infinity, right? It cannot go lower than 1. If you notice, it cannot go lower than 1 because the number of items I have in my corpus where this word occurs probably cannot be lesser than this. Okay, actually I can think of this, right? If you have 1,000 tweets where you have a very, very short number of words, okay, that's possible. But okay, let me revise this slightly. This is essentially going from 0 to infinity, right? It can go from 0 to infinity. Just like we use log in my term frequency to reduce the range, I'm using log over here to reduce this range, right? Generally, this is how people use it. Then the variants that I can have is basically these. I can have something which is known as the smoothened IDF, which is nothing but IDF of terms in the corpus, where mod D. Guys, just one quick change. This mod D over here is the absolute number of documents in the corpus, not the number of words. I'm really sorry. That was a slight confusion. What we should have here is actually 4. And while we were calculating the residual also, what we should have had is 4 upon 1. Okay. So mod D over here, mod D is the count of the total number of documents and not the total number of words, right? Which is what gives us the interpretation that this cannot be more than, this cannot be less than 1. So the range of these values actually goes from 1 to infinity here. Okay. The range of these values actually goes from 1 to infinity, which is why we apply log without any 1 plus. Okay. So from that point of view, if you notice the term here, this is the probability of finding a word in a given document. Yeah, sure, Rahul. I will definitely repeat this. Let us do this, right? Let us do this. Let us calculate IDF again. Right. Mod C instead of mod D. Yes, there is a slight change in the notation. Let me quickly update this, right? This should ideally have been mod C upon D. Yeah, okay. So this makes more sense now. I'll quickly update this everywhere. Yeah. So over here, this should be mod C. And this also should be mod C, right? Yeah. No, this is fine. This is fine. Okay, cool. So broadly speaking, this is what it has. Perfect. Thanks for that suggestion, Indradeep. Rahul, I'm now going to start repeating this. Okay. I'm going to paste this over here and we're going to repeat the calculation for our example. This is what I have. This is my IDF definition. I am looking for the IDF of the word residual with respect to document D1 in this corpus C. Okay. Now, this is nothing but log of total number of documents that I have. How many documents do I have here? I have 4. Right, Rahul? I have 4 documents. So 4 will come in the numerator. I have in the denominator, I will basically put how many documents are there where this word is present. So the word residual is only present in the ResNet paper. It is not present in the VGG 16 papers. So that is why I will put 1 over here. So this will be the IDF of residual over here, and IDF of network is going to be log of, okay, log of total number of documents is still going to be 4, but how many documents is it there in? It's there in all of them. So I'm going to put 4 over here, right? So now this is nothing but log of 4, and this is going to be in log of 1, right? If you notice, this is nothing but 0. This is somewhere in the range of, okay, what's log 10? If it's log to the base 2, this is just 2, right? So let's just see this 0.6, right? So this is somewhere in the range of 0.6. Okay, so this is what I have here. Now the question is, why did my residual word have a high weightage and why did my network have a low weightage? The reason is the word residual appears in only one document where it's important. So it is quite important in terms of identifying that document. The word network appears in all documents, so it's very commonly occurring, right? So finally, the inverse document frequency sort of gives me an idea of how important my word is with respect to my entire corpus. Cool? Does this make sense now, Rahul? Quick check. Okay, perfect. So now let's quickly look at the variants of this and let's move on, right? Let's quickly look at the variants of this and move on. Now my IDF of TDC is the this thing. So this is an explanation of all the terms which are there over here. And then here I have smoothened IDF, which is nothing but 1 plus. So now it could be possible that the word does not appear anywhere in the corpus, right? If I try to calculate the IDF for a term which is not there in my corpus by some mistake, maybe because of some mistake I'm trying to do this, it's possible that this denominator can be 0. So to correct for that, we have added 1 plus over here in the denominator and we're doing plus 1 here, right? So this has a tendency to smooth things out. And similarly, we can define something which is known as the max IDF, which is going to, instead of using the total number of documents I have in my corpus, I'm now going to use the documents in my corpus where this term is present. So the maximum number of documents where a certain word is present, that is what I'm going to start using in my numerator, and my denominator is going to remain the same, right? The count of how many documents is my word coming into, right? So this is how I can define variants of the IDF term. different papers will use different definitions. But now that we have understood term frequency and inverse document frequency, let us see how to implement it, and let us actually apply it to solve the problem that we have set out for ourselves, right? Okay, so let's go ahead and discuss that. So the implementation of IDF is very simple. Again, first I will create my vocabulary set. Okay, Amit, so guys, before I go there, Amit is asking me to explain max IDF. Amit, is it okay if I take this explanation to the doubt session? Could you please put up a doubt? I promise I will take the question first. Okay. So let's take it in the doubt session. We'll come back to this. Please put a question there so that I don't forget. And let's continue our discussion. Now we're simply implementing the most common version of this IDF. Okay. How are we doing that? Our vocabulary is again the set of all words. Inverse document frequency is defined as total number of documents, right? So the numerator is now going to be n, where n is the length of my corpus. Okay, so that is how I have the length of my corpus over here. The denominator I have num docs, where num docs is basically the count of all the words, the count of how many documents is my word appearing in, right? How many documents is my word appearing in? So that is what numdocs is calculating. So now as I simply take np.log of n by numdocs, we have a inverse document frequency vector. Okay. And once I do this, for this example, this is what I have, right? So if I do the IDF for this corpus, these three sentences, these are the terms that I get. So by casual observation, let us see what are the most important terms, right? There are a lot of words which have a lot of importance. Wisdom, foolishness, best, age, and worst. All of these have high importance because they appear probably only in one out of the three documents, right? By the way, do you guys know where these sentences are from? This is kind of interesting. The best of times, the worst of times. Do you guys know where it's from? What it's describing? Any ideas? Any readers of Charles Dickens? Okay, so if you've read Charles Dickens' book on the French Independence War, right? These are the first three sentences of that. So he describes the French Revolution as a time when there was the best and the worst. So there were these high-class people who were very rich and they were very comfortable, and it was the worst of times for the lower-class people. It was an age of wisdom, it was an age of foolishness. So again, the rich and wealthy were wise, and the hungry and poor were foolish. So it was a time where the difference, the gap between rich and poor was very huge, right? So it's a reference to that. Just thought it would be interesting to talk about it. Okay, anyway. So coming back, this is what our term frequencies, inverse document frequencies look like for each of the words that I have here. Now, if I combine them, the TF IDF is nothing but the product of both of these, right? So this function basically combines the term frequency and inverse document frequency as follows. It will calculate the term frequency for each word, it will calculate the IDF for each word, and it will simply multiply them. So a multiplication of this is what gives us our final TF IDF vector form, and this is what we get finally, right? This is what we get finally. What is interesting in this TF IDF form is, guys, we did not remove stop words here, okay? We did not remove stop words here. Do you notice that the stop words have very less weightage everywhere? So off actually appears in this, it appears in this, it appears in this. But off's weightage has actually become 0. Why has it become 0? Because its inverse document frequency is log of 1, right? Log of 1 is 0, which is why this has become 0. So one of the advantages of the TF IDF way of representing things is that most common words or stop words, something, see, the problem with stop words is we have to look at how words are used in the English language, right? But you could have some very common words which occur everywhere. So those words are automatically set to 0. And that is the advantage of using this TF IDF. It not only solves the problem of putting the right weightage on words, it will also make sure most common words are gotten rid of. So that the only words which survive are those which help us in identifying the importance of that document. Okay, so that is what we have left here. Cool. So once again, yeah. Indradeep says the name of the book is A Tale of Two Cities. Yes, that's right. It's a story of the French Revolution. Okay. So just as we had count vectorizer, which had a nice implementation in sklearn.feature extraction, we have this tf-idf vectorizer, which has some very helpful uh, options for us, right? It has some very helpful uh, uh, parameters which help us avoid implementing this earlier pipeline, right? This pipeline is kind of cumbersome to implement. If you specify the right things in this count vectorizer, it will automatically do the correct thing. Okay, so that is one reason why we would prefer to use the tf-idf vectorizer instead of our local implementation. There is one parameter that I sort of want to focus on. We are going to learn what n-grams are later, but I want to sort of justify the importance of this parameter over here. Okay, guys, I want to justify the importance of that. So let us look at a sentence. The iPad is not as good, is not good. Okay, is not good compared to previous releases. The new iPad, okay, let me say new iPad. Okay, cool. Uh, Anindya, yes. We generally do, Anindya. Yes. Okay. Coming back to this example, guys, if we had to do sentiment analysis on this, right? It's possible that we see this word good and it's possible that we conclude that this is a good sentiment, right? Just because the word good is there. The weightage of this not will go very low because it is commonly occurring in a lot of documents or reviews. But the word good helps us think that it is a positive sentiment. Isn't this a problem? Isn't it a problem that the not thing is not applying to this good here, right? So what we would normally want if we were doing sentiment analysis on this review, right? If we were doing sentiment analysis on this review and we just saw the word good and concluded it is a good sentiment, then it will be problematic. What we usually want is we want to take combinations of words to get the meaning out of it. So not good. So good is the opposite of bad, but it not good is exactly equal to bad, right? So the problem we're having here is by not comparing or not combining different words which probably mean different things. So this is where contextual information comes into the play, right? The context of this good is that it is not good over here. Okay. So the way people solve this problem is that instead of taking individual words, they will start comparing, they will start taking pairs of words. And this is what an n-gram means. N-gram. The idea behind an n-gram is instead of taking individual words, take pairs, triplets, quadruplets, etc. Right? That is basically why people generally tend to use n-grams. So what if I want to use the word not good together, right? I will have to set n equal to 2. So this is known as a bigram. Similarly, we can have trigrams and things like that. So we're going to be discussing this in detail. But what I want you guys to notice here is here I have an option of setting this n-gram range to something other than 1, 1. If I set it to 1, 1, it is going to only take the words at a time, one at a time. But now if I set this to 1, 2, what it will start doing is it will not only consider each unique word in as a part of my vocabulary, it will start taking pairs at a time, right? Yeah. Yes, Rahul Verma. We are using this to understand why n-grams is a good idea here, right? In my TF-IDF vectorizer, it's a good idea to use n-grams because we want to capture contextual information. The TF-IDF vectorizer over here, right? It gives us the option to set the n-gram here. It gives us this option. And that is why I'm saying it's better to use TF-IDF vectorizer, which has that option of using n-grams, right? In place of whatever we have. That's the idea. Okay, cool. Okay. So let me show you an example of this real quick. Okay. This is just one moment. Is this the one? Why is this not? Okay, no, this is not the one. Okay, one moment. We'll come back to this. This n-gram parameter I wanted to show you an example of. Yeah, so I just wanted to show you now that if I now set the n-gram parameter to 1, 2, what it will do is it will not only take the word, it will take the word and its next value, age of, and the best of. So it's not only picking up unique words from this thing, it is picking unique pairs as well, right? How many ways are there for me to make pairs? How many ways are there for me to make pairs in a sentence of length n? How many pairs can I make out of n objects? Come on, guys, we know this. Combinatrix, NC2, right? Yeah, NC2. In a bigram, that's not how we do things though. We don't take all possible pairs. We take all possible consecutive word pairs. So that is the difference. I wanted to bring this up because that is one confusion I used to have before. A bigram is defined as the consecutive words. So it will be it was. I cannot now use it and the in a bigram. It has to be it was only. Okay. So now can you tell me if I have a sentence of length n, how many bigrams will I have? How many? So this is, if you can think of this as convolution with a window size of 2. What is the output? What is the output? N plus 1, right? Viswarup has given me the right answer. N plus 1. It will be n plus 1. So yeah, this is how we're using convolution here to define bigrams. So that is, by the way, the link between convolution in our images and convolutions here. When we study n-grams, we'll sort of see that. Anyway, coming back, I can simply specify this n-gram parameter and I can get this whole job done. Okay, and it will give me this directly. Of course, the problem is that now the size of my vocabulary will explode, but that's okay. It's better to keep representations which are powerful than get rid of them, right? In fact, guys, over this course, we're going to study many representations. So today what we have done is we have done bag of words and we have discussed TF-IDF, right? Now, next class, we are actually going to learn something which is known as word-to-vec. Okay, we're actually going to learn something which is word-to-vec, which helps us capture these relationships between parameters, like pairs of parameters. Then we will move on to learn LSTMs, which additionally also keep in mind what the context which has been recently there, right? So this will be contextual information will be included here. And finally, we will slowly build our way to transformer models. So this is the most powerful. So this is like a slight sneak peek into what's going to happen over the next few classes. Today we're learning these two. Then we will see what all problems are there that word2vec will fix. Then whatever problems are there with word2vec, LSTM will fix. And finally, we will see how transformers is probably the best way to use embeddings for text. Okay, so we're slowly going to build our way there. Anyway, coming back, let's continue with our discussion. Okay, what is the drawbacks of this TF-IDF representation? Let us focus on this for now. Okay, so positional information of the word is still not captured in this representation, right? So like not good. The fact that good is appearing after not means it has some positional value there. That is not coming out in this representation. TF-IDF is also highly corpus dependent. So if I choose a corpus which is made of random things, this TF-IDF will not make much sense. So it's important to make sure that we have the corpus in mind when we're using this. And finally, a matrix which is generated from one corpus cannot be translated to other corpuses, right? So there's no way for me to compare a corpus of deep learning papers with economic papers or a deep learning papers with data science papers. Do you guys see that this is a problem for me in my current application? Do you guys see that it's a problem? The entire corpus of medium articles have all three categories. So that is the basic problem here. Okay, corpus dependency is one of the main drawbacks of TF-IDF. And another drawback which is common to both of them is the vocabulary size, right? Large vocabularies means larger length vectors. So slowly we will see how these new methods that we will learn over the next few classes, we'll see how they solve these problems. Okay, so let's just keep that in mind for the next few classes. For now, what we're going to do is we're going to go back to our task at hand. Okay, we're going to go back to our task at hand. Again, let us quickly revise the difference between Euclidean versus cosine similarity, right? Okay, so if you guys notice over here, I have three vectors. Okay. What I'm plotting here is the score of eggs and the score of disease in this space, right? So in a food corpus, eggs will have quite a few, will have a relatively high representation, but disease may not have a high representation in food corpus. Agriculture corpus, both will play a role. In history corpus, maybe disease will play a higher role, right? So what I want you guys to answer here is which is better. Should a food corpus be closer to an agricultural corpus or should it be closer to a history corpus? What do you guys think? What do you guys think? If I'm taking a food corpus, should I think a collection of food related documents, will that be more close to an agriculture set of documents or history? Agriculture, right? Okay. So now I want you guys to notice something. The Euclidean distance between this food and history is definitely shorter than the Euclidean distance between this food and agriculture, right? Visually, we can sort of make out that this distance is probably closer than this distance. But angle wise, this food corpus is closer to this agriculture, right? So if I had to choose between Euclidean distance and cosine similarity to work with my TF-IDF vectors, which we have so painstakingly created now, which one do you think is better? Euclidean or cosine for us? Cosine, right? You know why this agriculture corpus is larger? It's probably because of the size of the articles. So the magnitude of the vectors that we're seeing here has to do with the frequency of the vectors, the size of the documents and things like that. So artificially, the magnitude is being set by those factors. But if we want to check for similarity, right, it is a better idea to use cosine similarity with the TF-IDF representation that we have created so far. Okay. So what we're going to do now is we're going to apply everything we have done so far on our medium article corpus. We're going to find similar documents using cosine similarity, and we're going to see if it is a good representation system or not. Okay. So broadly speaking, now we're going to go back and we're going to solve the problem of recommending medium articles. Okay. We're going to go back and solve the problem of medium articles. Rahul's question to me is, how do we compare corpus? So Rahul, do you remember that the TF-IDF of eggs is computed for a corpus, right? So what I'm giving you here is the TF-IDF of eggs, disease with respect to the food corpus, with respect to the agriculture corpus, and with respect to the history corpus. So how do we compare corpus? We can compare it by calculating the TF-IDF vector for each corpus. So what we will do is, we will, so coming back, mathematically what I will be doing is I will be using this thing, right? IDF T, C. I will simply be changing the C everywhere. I will only change C. T and D are going to remain the same. I'm changing C over there. Got it? So that is how I can compare corpus. I can use IDF to compare corpuses. We need to do that for all words in corpus, more exact similarity. Yes. Yes. We need to do that for all words in the corpus. So of course, Rahul, I'm not going to use just two words. This was just for illustration to show you what Euclidean distance and cosine similarity means in our TF-IDF sense. I just wanted to display that. But now we're actually going to do this for everything in our corpus. So let's go to that now. So coming back to our original problem, like we sort of discussed this. Man should be very similar to king, but not so much to water. That's okay. Yeah. Let's now actually apply everything that we have learned so far to solve today's problem. Okay. So the broad steps that we'll be taking now to solve this problem is, we have our corpus, okay, which has document 1, document 2, document 3, and so on. Okay. We have 208 documents, if I remember correctly. What we're going to do is we're going to first get the TF-IDF representation. So we're going to do two things actually. We're going to compare bag of words with frequency, and TF-IDF. Okay, we're going to get both these representations. Once we get both these representations, what is the best way to see how similar articles are close? Like what is the best way to do that? Is it okay if I use something like TSNE plots to see how things are getting clustered? Now that I have a vector representation, I can apply TSNE on those vector representations, right? To sort of visualize how close similar documents are and how far dissimilar documents are. So this is what we're going to do in code now. Okay, guys, let's go over the code quickly. I'm quite confident you have already seen how to implement this on your own, right? You have seen how to implement TSNE or use TSNE in your ML2 classes. We just discussed in detail how we implement BOW and TF-IDF, and rest everything should be straightforward. So what I'm going to do is I'm going to slightly run through the code. If you guys want me to go slower, hit yes right away. Okay. If I go slower, I will take slightly more time, but I kind of want to rush through this code. Can you guys tell me what is a better approach? Should I take some time? Okay. Okay. So let me now kind of slightly go through this code really fast so that we can finally have some time to discuss the insights over here. Okay, cool. So let us discuss now. I have my medium articles here. I'm first going to build a pre-processing pipeline. Okay. Well, how are we going to pre-process it? We're going to split the article into sentences. For each sentence in the corpus, we're going to convert the sentences to lowercase, expand the contractions. Expand contractions is something we saw today's class, right? Things like couldn't and all that. We saw this. Then we'll apply lemmatization. We are not applying stemming here because we want to keep the word form same, right? We want these words to still mean the same thing. So we'll apply lemmatization there. We will remove the stop words. We will remove the punctuations. So all of these steps have been implemented in this function. Okay. You can see this here. Then what we're going to do is we're going to apply this for everything in our document. Okay. Now, guys, generally we use this package called TQDM. So it is pronounced as takadum, which in Arabic, I believe means, I forgot what it means, but this is an amazing thing which gives us this sliding bar, right? It gives us this bar which tells us how long it takes. So we implemented this to sort of show you that it takes 4 minutes and 40 seconds to apply this, which is why this was pre-run. So once we apply, so now what we're going to do is we're going to process each article in our corpus using this function. And if we do that for all 200 documents, it took 4 minutes, 40 seconds for this to complete. Once we have done that, let us go and actually start finding the similarity between documents. Okay. So now first I'm going to do it with bag of words. We're going to see what the results look like for bag of words. Then we will see what it looks like for TF-IDF. Okay. So again, bag of words, the best way to implement it is to use this count vectorizer rather than our own implementation. One thing that I have done here is I have said min df equal to 5, right? Let us go and understand what this min df equal to 5 means over here. So coming back to our count vectorizer, I want to focus on this parameter called min df. Okay. So min df is this. When building the vocabulary, ignore terms that have a document frequency strictly lower than the given threshold. What does that mean? It means that if my document frequency for a word is less than 5, then I will ignore that word. I will say that if my word does not occur in at least 5 documents, I don't want to consider that word because it may be some nonsense word, or it may be a word which is very specific to that document, right? It could be a person's name, or it could be a place's name, things like that, which maybe just occur in one place, but not overall. So that is why we are setting this min df equal to 5 over here. And then we are building our bag of word features. Okay. Just wanted to highlight this. The rest of it is pretty straightforward. You have count vectorizer.fit transform, which is applying, which we're applying to get these features. Then we're creating a data frame out of this. Our data frame looks like this. It's basically a 208 cross 3712 matrix. So guys, how do you interpret this 3712? What is this number telling me? What is this number telling me quickly in this data frame? It's the size of our vocabulary. Perfect, Rahul. This is the size of our vocabulary. It's the unique words that I found in all our medium articles. Okay, this is what we found. after applying this min df condition, okay, that is important. After applying this min df condition, we found there were 3,712 unique words. Okay. Now let's proceed. Once we have all of these, what we're going to do is we're going to apply TSNE to visualize how these different columns, right? How these different row vectors are distanced from each other. Specifically, the distance metric that we're going to use is the cosine similarity. Okay. Where am I doing that? Just one moment. Right. Yeah, so it'll be here somewhere in the code. I'm not able to find it right now, but we're essentially going to use cosine similarity to do that. So, oh yeah, C1 and C2. Yeah, that's how I'm encoding it here, right? Is that what I'm doing? Yeah. So I have these two things which, no, C1 and C2 here are the coordinates which TSNE returns, right? Yeah, in TSNE, cosine similarity is not used, but I can specify it somewhere. So Euclidean distance is used by default. Yeah, I see. Okay, I'll take it back. I believe we have not adjusted this to account for cosine similarity here. We have not adjusted that. What it will be using is Euclidean distance. I apologize for that. I thought we had taken care of it somehow in this code. I'll get this corrected. How we have to implement this now is the Euclidean distance, guys. Although cosine similarity would have been better, what we're going to do for our visualization is TSNE with Euclidean distance. So let's keep that in mind while we're interpreting things. Okay. So once I apply TSNE and I plot it, this is what my distribution looks like. Okay. So let us sort of get an understanding of how this distribution is. First of all, do you guys see any clusters forming? Are there any obvious clusters here? Yes or no? Guys? No, right? There are no obvious clusters here. But let us try and see if similar documents have similar meanings. Okay, so what's nice about this? So guys, to plot this, right, we have used this plotly.express. What's nice about plotly.express is it allows you to create this kind of an interactive plot. Okay, so if you notice what I have, if you hover over any of these, right, if you hover over any of these, you will actually get the title of the paper. Okay, so what I'm going to do is I'm going to sort of zoom into this place. Let me sort of zoom into this place. Okay, so here I have a collection of 4 documents. Okay, so this is like a mini cluster over here. Let us see if these documents are similar. So if I go to this one, this is what is a transformer. If I go to here, transformers explained visually part 2. This is transformers explained visually part 3. And this is how transformers work. So do you see that our bag of words model actually gave a similarity between these 4 documents? Is it obvious now? That our bag of words representation for our medium articles allows us to form a small cluster of all transformer related articles over here. Okay, let's go back and see some other clusters. Let's go and see some other clusters. Let's sort of zoom into this part now. So this part, guys, do you expect this cluster to be related to deep learning? Can we expect this to be related to deep learning somehow? What do you think based on this TSNE plot? I'm asking you to interpret TSNE, right? What do you guys think? This was deep learning. This guy was deep learning. So I'm asking you, is this also deep learning related? Yes or no question, guys? Yes. Why should it be deep learning related? Because this cluster which had deep learning terms is very close to this one, right? These 3 and these points are kind of close. So I would expect these 3 points to also have something to do with deep learning. Okay. So here I have understanding semantic segmentation with UNet, a comprehensive guide to convolutional neural networks. Machine learning is fun, deep learning and convolutional neural networks. See? So close things, so related things are actually close to each other. That is the takeaway that I'm getting from this. Okay. Now let us go to the other extreme. Let us sort of zoom into this part and let us see how these documents look like. So let me just get the zoom tool again. Let's sort of zoom into this part here. Okay. So since these 2 points here, right, they're very far away from the deep learning part. I don't expect this to be close to deep learning, but let's see. How I got a job in DeepMind as a research engineer without a machine learning degree. I interviewed at top 5 companies in Silicon Valley and got 5 job offers, right? So these articles are kind of related to how to get jobs in data science roles. So once you get this notebook, you can sort of take a look if you're interested in that topic, right? Uh, let's zoom into a different part again and see, try to look for that economics related clusters. So let's come here. Let's sort of study this cluster. So this is machine learning over here. So this is data science. So this part seems to be related to data science and machine learning. Let me zoom out. Let's try and look for those economics related articles, right? All that cryptocurrency stuff. Okay, it seems to be at the bottom here. Okay, it seems to be at the bottom here. If you notice now, at the bottom of this big cluster, Australia's economy is a house of cards, how to crush the crypto market, quit your job, move to paradise, do whatever you want. All these kinds of articles are coming at the bottom, right? So broadly speaking, I can take this cluster. Okay, let me do this. Based on my initial exploration, we have concluded that this TSNE plot, in this TSNE plot, we have all of these articles related to deep learning. We have these articles which are related to sort of data science. Okay. We have these articles related to job finding and stuff like that. Right. All of these articles are like job finding, and these are related to finance related things like cryptocurrency and like that. So broadly, we have spotted these clusters. So this is deep learning. This is data science. This is job interviews. And this is cryptocurrency. Right? So this is how we have successfully taken our corpus of Medium articles, and we have sort of put them in a space where similar articles are close to each other. Can we build a recommender system out of this? What do you guys think? Can I build a recommender system out of something like this? Yes or no? No? Why not? What's missing? I can, right? Okay, I guess why you're saying no. Okay, that was my mistake. Okay. So of course, this is not the best recommender system we can build, but whatever we have learned today is good enough to sort of build a naive recommendation system. That is what I wanted to highlight. Okay, cool. So now what I'm going to do is, so guys, this plot that we got, right? It used Euclidean distance here. But to do actual recommendations, what I'm going to do is, I'm going to use cosine similarity to do that. Okay. So if I now use cosine similarity, and for a given document, if I want to suggest the top 5 documents to you, let us see. Okay. So now what I'm going to do is get similar documents here is a function which is going to give you the top 5 similar articles for the input article. And we have run this for 4 random articles. Okay. So let's see. So now let us first look at the reference article, 17 types of similarity and dissimilarity measures used in data science. So this is a data science related thing. Let us see what recommendations it made. 9 distance measures in data science, 17 clustering algorithms, machine learning basics with KNN, over 100 data scientist interview questions, fundamental techniques. So all of these are related, right? So are you now convinced that we're doing a decent job of recommendation? Have we solved the problem? Yes or no? What do you think? We have, right? Let's take some more. TensorFlow tutorial part 1. How to go from Python newbie to Google certified, enchanted random forest, PCA using Python, 7 best data science using, 7 best data science podcasts, building RNN, LSTM, etc. Right? All this. Okay. So our recommendation system is doing quite well using just bag of words. Now what we're going to do is we're going to repeat the whole thing using TF-IDF representation. Okay. We are now going to see how good is TF-IDF in doing the same job. Again, I'm going to use the TF-IDF vectorizer where I'm setting the min df to 5 and I'm doing everything. This is for fair comparison. Okay. So once I do this, once I apply TSNE, this is the plot that I get, right? Do you guys see any obvious clusters in this plot? Any obvious clusters? Now in this plot, it kind of looks like we have one cluster here, and one cluster here, right? Kind of looks like that. So let's see what these clusters are now. So coming here, we have PayPal, froze our funds. So it looks like this part is the finance related part. So everything here is like finance related, if you notice. So algo trading, 26 rules I learned for crypto, introducing Ion Bank. This cluster seems to be that finance cluster. If I move up a little bit over here, I will soon start getting my data science related stuff here, right? All my data science related stuff is over here, like pandas, data frame, genetic algorithms, all that. Over here is where I have my this thing, right? Uh, like random topics, like something to do with yeah. So this is like to do with health and stuff like that. Okay, I had not even noticed that in the bag of words, by the way. I had not even noticed this as one of the clusters. And here we have the deep neural network stuff, right, at the bottom over here. So again, TSNE on the TF-IDF vectors kind of did a decent job of forming clusters. Once again, if we now try to get similar documents using TF-IDF features, let us see what the recommendations are. So now 17 types of similarity and dissimilarity measures. The recommendations I get is nine distance measures in data science, 17 clustering algorithms, machine learning basics, over 100 data science fundamental techniques and feature engineering. So these kind of seem similar. Let's see for the others, right? So let's go here maybe. How I lost 10 kgs in 60 days, my 7-step weight loss program. How to lose 10 plus pounds of fat in a month. 10 things you can do this morning to heal anxiety. Diet and workout plan. Science behind fat metabolism. Cure for type 2 diabetes. So yeah, all my health related articles are here, right? Okay. So main takeaway from this is that okay, so apparently there is an improvement in TensorFlow. Okay, let's sort of see that. So the suggestions for TensorFlow tutorial part 1 are how to go from Python newbie to Google certified TensorFlow developer, enchanted random forest, building RNN LSTM using PyTorch. Okay, yes, you should understand backprop and PCA using Python. Okay, so it looks like it's giving better recommendations for this TensorFlow article. So cool, yeah, fine. So finally, we're sort of done with the contents. I just want to go through some concluding remarks, right? Um, Broadly speaking, what we did today was, so let me sort of uh, put down my concluding remarks for today's class, right? So we started out by asking how to convert text to vectors. We studied two methods, bag of words and TF-IDF. Between bag of words and TF-IDF, what is the difference? Bag of words uses only document level features, whereas TF-IDF allows us to compare documents to whole corpus. Right? What are the shortcomings that we have studied in both of these methods? What is the one thing that we saw was not happening? Come on, guys. Can you tell me what is the one thing that was not happening properly? Anyone? Engrams? Ha, perfect, perfect. Indradeep, that your answer is correct for BOW, but Amit, give me the correct answer. Engrams, right? Context linkage was not happening, right? Perfect. So the shortcomings of this is context linkage is missing, and it is still sensitive. So not still sensitive. Let us say size of a representation, size of the vector depends on unique words. right? Okay. So what we're going to do now is next class onwards, we're going to see how to solve these problems, right? So broadly speaking, next class, we're going to be looking at something called word2vec, which basically gets rid of this problem, context linkage problem. After that, we're going to go to LSTM, which is a neural embedding, right? So it will sort of solve the problem of different sizes for different corpuses, right? It will probably give us a way to uh, find embeddings which work no matter what corpus you're using, right? And then finally, we'll go to transformers, which is like the most powerful way of doing things. So that is BERT. Specifically, we are going to be studying BERT architecture. So we're going to be moving towards that. And with that, like I'm done with the contents for today's class. I'm going to now start the doubt session. And I thank you so much for being patient. Yeah, I'm going to start the doubt session. I see that there's one question in the questions tab. I'll quickly explain that, right? It's Amit's question. He wanted me to explain the second variant of TF-IDF. Let me quickly do that now. I'll go here and I'll quickly explain the second variant of TF-IDF. Hold on. Let's go back to the math. Yeah, here we are, right? This is the max IDF. So let's sort of take this and understand this equation. Okay. So what we're going to do is we're going to study the numerator and denominator separately. Okay. So first I'm going to focus on the numerator. So in my normal IDF, Amit, the numerator of my IDF term, right, is going to be the total number of documents in my corpus. Number of docs in corpus, right? This is what my IDF's numerator was. Here we are replacing this thing with this. So let us see what we're replacing it with. Max of T prime in D, okay, over what? Max over what? So I'm going to take a max over all the terms in a given document, okay, where I'm counting the document in a certain corpus such that term is in that document, okay? Okay. So now let us try and understand this. This part tells me over all documents in corpus, find if T prime belongs to D. Right? Okay. So essentially here what I have in the numerator is I'm going to look at every document in my corpus. In that, I'm going to basically look at whether that term is there in that document and I'm going to take the count of it. Okay. So let us say we had four, again, let me use a very simple example. I have D1, I have D2, I have D3, and I have D4. Just like before, the word residual appears here and the word network appears everywhere here. Okay. The word network appears in all of these documents. Okay. Now let us see what this is. So what this numerator means is I'm going to now look for one term. So the maximization, if you notice, is happening over all the terms in my corpus. Okay. That is where the maximization is happening. I'm now going to ask, find me that word which has appeared in the most number of documents. So how to interpret this is find me the word. Sorry. Instead of that, a better way to frame it is how many documents does the most common word appear in? What does that mean? Okay, so let me change my example a little bit. It will be sort of easier to explain if my network appeared only in D1, D2, and D4. Let us assume this D3 is not related to neural networks, it is related to SVMs. Okay, so let us say this D3 is an SVM article. What I now have in the numerator is this term, right? How to interpret this is the word network has appeared in 3 documents. Let us say no other word appears in all 4. Okay, let us assume no word appears in all 4. Then we have network which is appearing in 3. And then let us assume all other words don't appear anywhere else. Okay, so over here, what I will put in the numerator here in this example is 3, because I have this network which is a term which has occurred in the maximum number of documents here, right? So if you notice, what we have done here is instead of taking the total docs in corpus, what I'm going to replace it with is how many documents do I have which share words, right? The maximum number of documents I can get which share words, like that. Okay. So when is this useful? Right, Amit? That's a very good question to ask. When is this useful? This is useful when I have a very varied corpus. So for example, in today's corpus, we saw that there were health related articles as well as deep learning articles. So if I use the normal IDF over there, uh, it will lead to an IDF score which is much higher than I expect. Why is it higher than I expect? Because I'm taking all the documents in the numerator. Instead now, let us say for the deep learning articles, I wanted to look at the IDF with respect to only words which are there in that cluster of deep learning articles. So that is why it would sort of make sense to adjust this number for words which are common to just deep learning articles. So max IDF is simply replacing the numerator with the uh, count of the documents which share a word, the max count of documents which share a word, right? And it is useful in situations where you have a very disassociated corpus, in the sense that a corpus which contains many documents of many different types, right? That is where I would use this max IDF instead of IDF. Okay. Yeah. Amit, I have unmuted you. You can please go ahead.
Hey Dhruv,
Hi.
in
Yeah.
this, right, if you see numerator and denominator, right, in the
Yeah.
numerator we are talking, uh, this
Hmm.
IDF will be calculated based on for the specific word, correct?
Yeah.
In the document. Now, let's say you have a four
It's for a specific word in a corpus. It's
specific word,
yeah. Hmm.
specific word in a corpus.
Hmm.
Now, in the numerator we will have the most frequent word occurring in the all possible documents, right? That will give them. Let's say in
Hmm.
out of four documents, three documents have the most common word. So that is
Yeah.
coming three here.
Hmm.
Now in the downwards, what we will in the denominator we will have in which that C
Hmm.
is C has been occurred, right?
Hmm.
So let's say the C is occurring again, uh, let's say in 2. So numerator doesn't have any relation with the word, the word in the corpus.
Correct. Correct. Numerator has no relation with the this t over here. So you are
Oh,
calculating IDF for a t.
yeah,
The
yeah,
numerator will have no relation to that t. It will have a relation to the word which appears in the maximum number of documents.
got it. Now I
Yeah.
understand. That's the
Yeah.
confusion I was.
Ah, I see. Yeah. So the way I understood this was, see, this there is this t prime, right?
Hmm.
That prime is telling me that these are different from these t.
Oh, got it.
Yeah. Okay.
Thanks.
Cool. You're welcome. All right, guys. So that answers this question. If anyone has any other questions, I'll wait for a while. If not, we can end today's class, right? I'll just hang around for a couple of minutes in case you guys have any other questions. Otherwise, we will resume next class where we will be discussing word to word. Okay, Akash has a question. I'll quickly unmute him. Please go ahead, Akash.
Hello, able to hear me?
Yeah, yeah, I can hear you.
Sorry,
Yes.
I got disconnected while I was
Ah,
solving his doubt for that max one. I just
okay.
want to confirm on it whether my understanding is correct or not.
Sure, sure, sure.
For the IDF, for
Hmm,
the normal IDF, we will
hmm.
take the um, number of words in
No,
in a document divided by in number of documents, that word which we are gonna take it, like,
Yeah.
is there? Is it
Just
right?
one. No, this is not right. What we have in the numerator is the total number of documents in the corpus. So this is one bug we found while I was discussing. What was written here before was mod D. I corrected that to make it mod C. So now in my numerator, what I have is the total number of documents I have in my corpus, right? That's why it's mod C now. It's not the
Okay.
total number of words in that document.
Okay. Okay.
So
Got it.
yeah. I can
So
actually
the
get rid of this.
denominator will be is number of
Uh, documents, this word is present
this
in.
word is present. Okay.
Yeah. Number of documents, this word is present in.
Okay, so in the max time, so then my understanding got a bit confused. Sorry. In the
Oh,
max,
no worries. We're here to solve doubts, right? Let's take it up. So in the max one, yeah. So
yeah,
see here. Uh, is it okay if I go to the example and explain once, and then we'll come back if you didn't understand?
yeah, sure. Yeah.
Okay. So now, if I was not using max IDF, okay, and let's take this example. I have 4 documents in my corpus. 3 documents are about neural networks. 1 document is about residual neural networks. Let's assume these 2 are for VGG, and this one is SVM. Okay. So let us now assume that the word network is appearing only in these 3 documents, D1, D2, and D4, which are the deep learning documents. In D3, it is not coming because SVMs are there. So why should network come there, right? So we have that. This is the example. If I was doing IDF normally, what I would put in the numerator is 4. If I was doing IDF with max IDF, I would actually put network, the count of network, which is 3.
Okay.
Yeah. So what I'm basically counting is how many documents are there, maximum number of documents which share words. That is what I'm after.
Okay. Got it.
Yeah.
Isn't it will be the same for everything, every group, like for all the documents?
The IDF will be, see, the IDF is a function of the term and the corpus, right? Corpus we're
No.
keeping fixed. So IDF will change with the term that we're calculating it for.
Okay. Only the numerator will be same, denominator will be changing according to the different words. Okay.
Correct. Absolutely
Okay.
correct,
Got it.
Akash.
Yeah. Thank you.
Absolutely correct. Yeah, you're welcome. Okay, cool. Any other questions, guys? If not, we can end the session here, and I will see you guys on Monday. Cool. Okay, guys. So good night. Have a happy weekend. I'll see you on Monday. Hope you enjoyed today's class.